To my immediate right is Jim Lynch, who is with Geoenergy Services. And to his right is Norm Weaver, who is with the City of Fort Collins, and a senior energy services engineer. They both have a long list, as does Scott Denning, a long list of credentials. So if you would just take a minute and tell our audience here tonight what in your education, your experience, your research has brought you to the job that you're performing today.
My background is I'm originally a civil engineer, graduate from Purdue University. Within 3 months of graduation, moved to Colorado and have been here ever since. I was a building contractor, owner's representative for about 20 years, general contractor, but we look for a lot of large general contractors here in the state. And about 10, 12 years ago, started learning a little bit more about geothermal and exactly what this product was, and just it really quite amazed me, and what the ability that these heat pump systems are able to provide, and the energy savings and the clean energy to what we're doing. And so, hence, I started the company about 10 years ago. Started with most of our projects were high-end homes in Aspen and Snowmass for a number of reasons. And because of the economy shift here in the last probably 5 or 6 years, the majority of my business has been large commercial projects. Because of the downfall of the economy since 2008, I'd say 80 to 85% of my work is all government, municipality, military bases. We work everywhere from Kansas to North Dakota, as far south as Arizona. Just had to spread our wings that much. Geothermal is a relatively small segment of the entire construction economy. So when the entire construction economy goes down, our small segment gets smaller. So we've had to spread our wings, and we travel quite a bit. With that being said, we've got over 400 successful systems up and operational in the western United States. Finished up quite a few right now. I just left, came back from one Air Force base on the way back this afternoon for this meeting for another, probably our 5th project we've done up there. The military and the school districts have really embraced this technology. And I'll get into a little more of a Geothermal 101 class I'm going to give you folks this afternoon or this evening, and go from there.
Good evening. I'm Norm Weaver, as indicated with City of Fort Collins Utilities. First off, I'd say what a great turnout. Glad to see you all here. This is, I think, an important topic, and glad that you responded to the information from the league. I guess a little more than 30 years ago, I was a graduate student at the CSU Solar Lab, which was out, west on LaPorte. Half a dozen solar homes out there, a number of members of the faculty at the college at the time that were really in the forefront in the country in terms of looking at what solar technology was about at that time. I'm a mechanical engineer by training. I apologize in advance. You may have seen from the handout, we like graphs and things like that. But I think there's some important things to talk about here. Since those bygone days at the CSU Solar Lab, I've continued to be involved in energy analysis in buildings and residences, and most recently, when I came back to Fort Collins, working with the utility, we have, I think this community has the good fortune of having a good progressive municipal utility, and I joined at the time about 6 years ago a very strong energy services group that was attempting to offer education and incentives for energy efficiency and starting into renewables, and more recently we have been increasing offerings for solar technology, which is one of the things I'll be trying to talk about tonight.
What our technology does, we are passive geothermal as opposed to active geothermal. We are not drilling 2,000 to 4,000 feet in the earth looking for steam aquifers. We're not the Glenwood Hot Springs. What we're doing is taking advantage, because what they do with those products is basically bring the steam to the earth surface, flash point, run turbines, and generate electricity. We are not generating any type of electricity at all. What we're doing is using geothermal to heat and cool with closed-loop refrigerant heat pumps, which I'll get into here in a minute, to basically take advantage of the fact that Earth's a big warm solar collector, big warm rock. Once you get below frost line in Colorado, you're typically between 45 and 52 degrees year-round. So what we're doing is basically tapping into that energy. With the use of the heat pumps, we're able to basically switch energy, heat and cooling, back and forth, just with the use of electricity and pumps and the heat pumps themselves. Very simply, think of it the way your refrigerator works. Your refrigerator is an air conditioner. It's not taking the air from inside your house, making it cold and cooling your contents in your fridge. Rather, what it's doing is using a refrigerant and a compressor to extract heat from the space, BTUs. So if you put your hand in the back of your refrigerator, you feel that heat coming off the back of it. That's exactly what heat pumps do. That's what a heat pump is. And so we're just taking that and applying it to residences, homes, commercial buildings, any type of structure you could imagine. We've done probably over 400 structures in the last 10 years. So that being said, and hopefully, our term we use quite often as a trade name is called geo-exchange or closed-loop geothermal heat and cooling systems. So with that being said, there's one of our logos. The EPA is a very strong proponent of our technology. As the EPA stated, this is over 10 years ago, geothermal heat pumps are the most energy efficient, environmentally clean, and cost-effective space conditioning systems available. That remains to be the case. Government studies have shown that geothermal systems have the lowest life cycle impacts on the environment of any HVAC system available, as well as the lowest life cycle costs. Geothermal, also known as geo-exchange or GSHP, ground source heat pump systems, use the Earth's energy storage capability to heat and cool buildings and provide hot water. The economic stimulus bill now provides a 30% tax credit for residential geothermal projects in the form of a tax credit and a 10% rebate on commercial projects through 2016. And I suspect that'll probably be continued once it comes to expires. The basic benefits of geothermal heating and cooling systems are lower life cycle costs, annual energy and cost savings, large summer peak load reductions for utilities, and that's why Xcel and some energy companies will help support these to extent in the fact that when you think about peak load restrictions and reductions, peak load in most power plants being built these days are for peak loads. So when it hits 90 degrees at 2 in the afternoon and everybody's 90% of the air conditioning in the state turn on at once, boom! All of a sudden we need 3 times the electrical power we need the rest of the year. Because of the fact that we're using the Earth as a basis of the heating and cooling source, and that's a constant, there's no need for that to happen. The ground source heat pump system in the Earth doesn't care what the ambient outside temperature is, therefore it doesn't affect it. Longer lifespan, heat pumps typically last 20, 25 plus years. And the loop fields we install, they're warranty. They're actually the manufacturer warranty. The material we use is 50 years, and we suspect they will last 80 to 100 years. The only thing that really causes these to fail is when people dig into them, and that happens every once in a while. Reduction in greenhouse gas emissions. Potentially 6% of current global emissions are being reduced right now from the current use of geothermal heat pumps around the world. And again, it is a renewable, endless green technology. As long as the sun keeps coming up and heating up the Earth, well, we'd all be gone if that didn't happen, but nevertheless, the technology will remain viable. The roadmap of the industry, here's what we've kind of seen happen in the last few years. In 2009, there were 100,000 ground source heat pump installations per year, public-private entities, and the plan is to increase that, and the government's trying to help mandate that to 1 million installations per year by 2016. In the U.S., the industry grew at a rate of 40% between 2004 and 2007, and ground source heat pumps remain a very small percentage of the U.S. HVAC market, as I alluded to earlier. Current growth rate is approximately 32%. And when the economy comes back, we can probably see that a little bit more. China and a lot of foreign companies really embrace this technology to the point where we're kind of embarrassed when we look to see what they're doing. China introduced ground source heat pumps in the 90s. And in a 5-year period, from 2004 to 2009, the market grew 1,200%. So it's been amazing. The European market and the Canadian market has always been light years ahead of us, and has consistently grown at a rate of 10% since 2007. And I'm going to kind of say this tongue in cheek, excuse me. I hope there's no oil and gas people in here, but a lot of people ask me, Jim, well, why isn't this growing? This is such a great deal, and this is such a great technology. Why isn't it growing more? And I think a lot of it is most old school engineers, or most people in general in this country, feel that unless you're burning something or combusting something, you can't generate something. You can't generate heat unless you're burning fossil fuels. And we're trying to prove just the opposite of that. in it, and it takes people, it's kind of like I'm in Missouri, the show me state. I've got to get one or two up running for a client. School District 17, or 11, excuse me, down in Colorado Springs, they were an ideal example. We started working for them about 8 years ago, retrofitted one school. They sat back and watched it for a year, and over the course of the next 4 years, almost every school in Colorado Springs School District has been converted to ground source heat pumps. And all this data is from NRAIL and DOE and all these good government entities. So here it is again in a nutshell. The Earth's a large solar collector, absorbing about 45% of the sun's energy on a daily basis, and it stores it acting like a solar battery. What you're doing, you see my little stripe building and my vertical geothermal wells in the ground. What we're doing is we're taking that passive geothermal energy, those BTUs, and flipping it back and forth within the building itself. The three primary components of a geothermal heat pump system are the heat pump itself that moves the heat between the building and the fluid and the earth connection. The earth connection being the loop field, which is what we design and install, which is used for transferring heat between the fluid and the HDPE piping itself and the earth. And then a distribution system for the heating and cooling, very similar to your radiant floor heat, your ductwork. That's very typical with any HVAC system, same delivery methods. This one will probably be easier for me to stand up and kind of point this out, but again, this is very simply how a heat pump works. This is in the heating mode. So what we have, and I'll show you some pictures, I have all this plastic pipe buried in the ground. And it's coming in as the red fluid here. That fluid is typically a mixture between propylene glycol and water. What happens is this energy, because water comes in at about 50 degrees approximately, we'll use for example, goes into a pipe heat exchanger, okay? So what we got is on the outside of the pipe, we have 50-degree water flowing through there. On the inside is refrigerant. This refrigerant boils at a very low boiling point. So what we're doing is we're using this energy. What enters this 50-degree water will exit it at about 58, 56 degrees, and while it sucks that energy out of it, we're boiling that refrigerant. That gas then goes into the compressor. We compress the gas. That heats up to about 180 degrees. At that point, that gas then goes into another coil and coil heat exchanger, and we heat up either water for hot water heating systems. That gas does get to about 180 degrees, and it allows us to heat water to about 115 degrees. So with that, one or two systems, we run that water through your radiant inflow heating system and heat your home. Or we actually, if it's a forced air system, we'll actually run that through a fan coil and draw the air from the building itself over that and heat the building that way. As that happened, everything starts cooling off, goes back to a gas again, or back to a liquid again, excuse me, then the entire system repeats itself. It's kind of a perpetual motion machine, if you will, once you add electricity to it. And this is it in the cooling side, just like I explained earlier. Hopefully that sometimes that refrigerator thing helps people understand things a little bit better. But basically, it's the same scenario, just working in reverse. This reverse refrigerant valve is we're using this refrigerant, we're taking the heat from the space, we're dumping it back into the loop field. Okay, so what we can see is during the heating season, we continually are drawing heat out of this water. We design our loop field temperatures to go no lower than 30 degrees in the wintertime. In the wintertime, we can get down 45, 60 degrees is our sweet spot, if you will. In the summertime, on an extremely hot summer, couple months, we continue to dump heat in the loop field. That loop field water can get up as high as 90 degrees at design temperatures. So you can see there's quite a bit of fluctuation. And so a lot of people say, well, the pressures are changing a lot. I'm like, well, it's because the HDPE pipe's expanding and contracting every time we change the temperature of that fluid. Doesn't mean you have a leak. Here, I can sit back down for this then. Did anybody have any questions on that? Because that is really the backbone of these systems. Yes, sir.
Does the closed loop system have to interact with groundwater?
No. We've been requested, and we have done some open loop systems in other states, but our regulatory commission here is Division of Water Resources, or GOD, as I like to refer to them in Colorado, Denver Water. And they are very, very particular and concerned about us drilling these 400 and 500 foot holes and contaminating aquifers. And so that's why typically the easier permit and 95% of the systems going in the state of Colorado are closed loop systems. And what we do to prevent it, because we obviously do drill through aquifers, but basically, and I'll go through this a little bit further, is we'll drill the hole, run the plastic pipe down in it, and then grout the hole back solid, so any aquifers we might have gone through is basically being sealed off. Just a few facts here. and there's a few I don't know if there's a few engineers in the room that might understand these terms, but a ground source heat pump extracts heating or rejects cooling 3 to 5 times more efficiently than anything else out there. So basically, what I'm trying to say is you go to Home Depot and you buy a boiler that says it's 90% efficient. Okay, so you're going to throw every dollar you put in that boiler, you're going to get 90 cents with the hot water back out of it. In a geothermal heat pump, every dollar you throw in electricity at the heat pump in the system, you're getting $3 to $5 worth of cooling and heating back. It's about twice as efficient in the heating mode and about 3 to 5 times more efficient in cooling mode, which really plays well in Colorado because, believe it or not, even with our supposed cold winters, most of these buildings are cooling dominant most of the year, given the sun loads and then everything else, and the people loads and the computer loads and light loads. You'd be surprised. So again, your COP has been between 300% and 500% for heating. Your EER is 14 to 20+%. Those numbers may not mean anything to anybody. And SEERs, how they rate air conditioners, that's 18 to 25. Again, it's all multiples more improved over conventional systems. So here's kind of an example, and the rest of these are basically just pictures of jobs that'll give you an idea. You can kind of really get a taste for what we're doing. This is an example of a heat pump for a radiant in-floor heating system for a residence we did quite a while ago in Aspen, Colorado. And the component you're looking at here is basically these pipes coming through the wall. That goes out to our loop field. This is our pump pack that flows the water from the loop field into the heat pump. This is about a 5-ton heat pump. That's all the larger these units are, which is another real nice thing about these. Don't go outside. They don't go on the roof. You don't got to increase structure loads or build parapet walls to hide unsightly equipment. Everything fits in the mechanic room, vandalism-free, isolated from weather, and again, hence the longer lifespans. Besides, the equipment itself has very few moving parts in it. So once the water goes in here, the heat pump does its magic. It's putting water. We take it in an old hot water heater and convert it into a water storage tank. And at that point, the hot water comes out and goes to each individual zone as it's calling for heat. Okay, this is a job up near Fraser, Devil's Thumb Ranch. And this is an example of a very large convention facility where these are 12-ton heat pumps, and we were able to hook these up in series to meet the load of the large building. The reason for this is, we've done jobs as small as, 1,200 square foot homes to as large as, 150, 200,000 square foot buildings. There's really no limit to what these systems can do as long as they're designed properly and installed properly. Okay, here are the capabilities. What can we do with geothermal systems? Obviously, space conditioning I've been talking about considerably, being forced air heating or cooling or radiant floor heating. Domestic or potable hot water, being your domestic water for your showers and your dishes or your hot tubs, pools and your spas. Snow melt, I'll say that kind of, again, tongue-in-cheek, and because that's pretty expensive. Snow melt, I kind of shake my head when people want to do snow melt because it's one of the largest wastes of energy on the planet that I'm aware of. I mean, you're basically heating up your concrete when it's 20 degrees out or 0 degrees out because nobody wants to snow or plow the snow away. I'm not going to go any further on that. Process water conditioning. We've done some work actually in like chicken farms and dairy farms where they need hot water on one side of the building and cold water on the other. And we're able to use heat pumps to swap that back and forth and greatly reduce their energy bills. Ice making, being thermal storage, being ice rinks, thermal storage, cooling systems, the IKEA project we did. What they do is obviously, and I don't know how familiar with Excel, but it's cheaper to buy lots of electric energy at night when there's no peak load demand and very few people are using that energy. So what we've done over there, and we didn't design that, rather we installed it just to make sure everybody's clear on that, is they've designed that where basically they make a big cooler full of ice every night when they can buy power cheap using heat pumps. Then during the day, they basically draw the coolness off that ice and use that to cool the building. Because again, that's totally a cooling dominant structure. We also can recycle heat from other applications, being refrigeration and ice making. For example, again, what's the byproduct of making ice? You drive by the Pepsi Center on a cool day, you see that big plume of steam. That's BTUs. That's energy just going in the atmosphere, just totally wasted while they're burning gas like crazy to create that. What we're able to do, and a prime example is the Conoco Wendy's up in Frisco. Is Danny, and again, another engineer designed this one. I won't take credit for that, but we did install the loop field. What they're able to do is they capture the heat off the back of their coolers for their beer and the coolers for the Pepsi and the coolers for the ice machines. They capture that heat and they send it over to the car wash, and he gets free hot water year-round for the car wash. It's just, it's unbelievable. I mean, he just couldn't believe the amount of money he saved. And then again, load sharing between, in similar buildings, load sharing between different zones, being you're in this building on a cool winter morning, the whole building's calling for heat. By the time noon hits and this side of the building's getting baked, this side's still calling for heat, this side's calling for cooling. So what we're able to do is swap it back and forth, basically, just do it through a racetrack of ductwork. Again, you know, our real goal is to try to use as little energy as possible. Before I go into that, I took a few slides out of this to speed this up a little bit because I can talk forever. Basically, at the end of the day, we're reducing your electric bill between, or your overall energy consumption bill for your structure between 50 and 60%. The primary reason for that is there's no need for natural gas any longer. Your electrical bills do go up a little bit over a conventional system, but because you're not buying any gas at all, it balances out to a net savings. Okay. Now, the second connection that I talked about earlier is this is the closed loop geothermal loop fields and the type of loop fields we install, well, that are installed, period, that are approved. Vertical, being where we drill holes anywhere between 200 and 500 foot deep, run the U-bend down and back up, grout the hole solid, run it into the heat pump. Those are probably the most common on large commercial projects because of lack of land. And it's just a matter of how much space. I mean, all this is, at the end of the day, it's a factor of how many linear foot of pipe do you have in contact with the ground, how quickly can you move heat and accomplish what you're trying to do. You also have slinky or pit loops, which is basically we dig a big hole. We dig a big hole 8 to 12 foot deep and lay these things out in a coil configuration. And I'll show you some other large ones we've done, and then backfill that. That can be a lot more cost effective if you've got a lot of large area to work with. It's less expensive than drilling, and especially being in the Rocky Mountains, drilling conditions are always not very favorable. I mean, I've had a few high-end homeowners come to me and say, Jim, you know, why couldn't you guarantee me this drilling price? I was like, you know, you're in the Rocky Mountains. I mean, if you wanted to budget in the cheapest geothermal system you should have done, you should have built your trophy home in Kansas. And then I don't enjoy that very much, but it's reality. We've done quite a few pond loops. You know, basically, if you've got a large body of water, I mean, heat exchange from water to water is obviously more efficient and more effective than trying to push heat from water to dirt. And so if we got a large pond or a large body of water or a lake, we basically just throw either a plate and frame heat exchanger out there, being a glorified stainless steel radiator, or we'll just bury the slinkies at the bottom of the pond, put a little ground cover over there, or a pond liner so nobody's out there fishing and doesn't pull it to the surface and causes some problems. And then on smaller residential projects, you can go the simple horizontal system where it's similar to the slinky lift system in that you dig in a trench and you're just laying the pipe in the trench itself. And again, you know, that we like to be about 8 to 10 foot deep, depending on where we are in the state of Colorado and the climatic conditions. Okay, here's a few examples of some projects. You guys may not have known, the IKEA store is 100% geothermal. There's 130, we went out there and drilled 130 500-foot deep holes underneath the parking structure before they started building that building to heat and cool that. And that system's been up and running for well, a year or plus now with no issues at all. This is a picture of our drill rigs. Our drill rigs are basically water well drill rigs that have been converted for geothermal applications. It's drilling. It's a muddy, messy job, and if my guys aren't knee deep in mud, they're really not very happy. That's just the profession. It's drilling and it's messy. But what you're seeing here basically is the drill rigs there. This is an example. That's what a pile of cuttings, drill cuttings, looks like that comes out of a 500-foot, 6-inch diameter hole. And then this is our grout line and our grout or our sand and thermal grout mix that then we fill the hole back up with. Let's seal it up. Bill Roberts School, Denver Public Schools. We've drilled 230 300-foot vertical wells at that school. That was done quite a while ago. That was one of the first Denver public schools we did, and quite a few have followed since then. Green Valley Ranch campus, that's all geothermal, all those buildings out there. Here's another job. Here's another picture of just a bunch of our equipment and trucks, and we had our 4 drill rigs out there, you know, flying the colors and getting that job completed. Okay, so after we drill these holes, and if you take a look at this right here, that represents the top of 2-inch-and-a-quarter pipes coming out of the top of a 500-foot drilled hole. So then what we do is we go in and we excavate this trench and we manifold these together horizontally in a reverse return configuration with the pipes being sized up and then sized back down, so basically these circuits self-balance. And we want to make sure we push just as much water to the very last loop as we do to the first loop. And that's where the balancing comes in. On large jobs like this, quite often we'll do vaults, whether it be HDPE, which is what this vault is, high-density polyethylene, that's the material we use, which is a little ironic, but I get a kick out of it. This is the same exact material, except it's black and has geothermal stamped on the side as the yellow gas pipeline you see being installed in neighborhoods. Same heat fusion properties. My guys go to the same heat fusion schools as the Excel guys go to learn how to melt this pipe together. I did see the one they're replacing out here is steel because of the size of it, but a lot of natural gas has gone with the HDPE pipe because it's a very indestructible material, very tough. So that's the outside of the vault. So what we're doing is at each one of those circuits I showed you earlier, a supply and return line comes in. The red indicates supply, the green on top, we haven't connected those pipes yet, that's return. And basically each one of these represents a string of 12 500-foot holes that runs into the vault. We then manifold that in the vault, run into this 8-inch pipe. As you can see, I'll come in with balance valves and circuit setters so we can adjust and balance everything. At the very far end, you see the 2 brass valves. That's our flushing and purging ports. So we can clean the system out and purge it of all the air and induce the glycol. And what this does is most of the manifolds end up in a mechanical room and take up quite a bit of space. This one we've got buried out in the back 40, and all we got to do is run 2 8-inch pipes into the mechanical room, and they tie that in their heat pump systems, and that's what runs the building itself. Joint Forces Readiness Center up in Cheyenne at Warren Air Force Base. Again, 240,000, 1,000 foot slinky coils. And we'll take a look at this. We dug a hole that was literally almost 12 acres in area, basically 10 foot deep. And you can see each one of these represents 1,000 linear foot of pipe all coiled up that then would come back in and backfill back up to about that level when we're done. And they seed it and put a parking lot over it and it's done. And here again, here's our equipment in action there, moving a lot of dirt. And we've even got like a B-52 up in the sky there I was able to catch. Unbeknownst to me till I looked at the picture. I mentioned Green Valley Ranch Elementary School. Again, that's in our series of pit loops underneath the baseball fields and the football fields. That's something else to be thought of, and that's why I brought up IKEA. Is people say, well, can you build on top of these? What's going to happen? I'm like, well, when we bury these systems 6 to 12 foot below grade, anything going on top of them, as long as you're careful with it. Our biggest issue has been people drilling light pole bases that say, well, you're 6 foot down, my base is only 4 foot deep. They take that auger drill and do one last spin to clean it out. Next thing you know, they're right into our loop field, and we got black plastic coming to the surface. But again, that loop field that I showed you earlier, it's a parking lot over the top of it. We got parking lots, football fields, baseball fields, buildings, and whatever you can imagine goes over the top of them. And there's the Green Valley Ranch project right there. And you can kind of see the cut on the side here. This shows you the depth of where the finished grade's going to be, pretty much about a foot or two above my guys' heads there. Just another view of the same project out in Aurora. Let's see here. An example of a concrete vault. HDP, supply and return lines going into the header of the manifold, and it just happens to be concrete rather than HDPE. There's the inside of the vault with the circuit setters and the valves and everything else, all the good stuff you need there to make that work. And again, that guy all gets buried and covered, and all you see is a manhole at the end of the day. Gateway Auto Museum. Now I'm getting to a few pond loops. This was an interesting project down in Gateway. I'm not sure if have folks ever been to Gateway? It's south of Grand Junction. John Hendricks, the owner of the Discovery Channel, he used to go there as a boy hunting. And once he got rich and famous and successful, he decided to build his dream home and create a community. And he's basically bought and built the town of Gateway. And what he's got down there now is a large automobile museum that houses all of his collector cars, which is just amazing. But nevertheless, it's geothermal. When we went down there, yeah, he's got all those cabins down there hooked right alongside the. And if you drive, you can go down there and stay in a cabin or stay in a hotel room. And it's what his thought was is to try to get the people, the collecting car people, especially that are going from Junction to Moab to drive the back way, and Gateway is kind of a midway point, if you will. It's a beautiful area, but very, very remote, very remote. As you can see in the background, those are just the stucco buildings they're building right there, and those are the. But nevertheless, we got out there a few years ago, and he's like, Jim, I want you to drill us a test hole and give us a price of what it's going to cost. Well, the drilling was just horrific. It was just cobbles and shells. We were right down by the river. Everyone's caving in. I was like, it's going to cost a lot of money to do this. And we're looking at the plans, and I'm like, well, what's that pond there? He goes, well, that's our irrigation pond. I'm like, is that going to be full year round? And he's like, absolutely. And so what we decided to do is go in and layer coils in the bottom of the pond, cover it with a pond liner and some dirt right there, and then fill it up with water, and there's your closed loop heat exchanger right there. That's what it looks like at the end of the day. That's kind of the unsexy thing about my job is when I'm done, you don't see anything. It's all buried. Typically on new installation costs, all the additional costs is the cost of the loop field. Heat pumps, duct work, that all same costs about the same, within 5% as an air conditioner or a furnace. All your additional cost is in the loop field itself. And typically that can be about 50 to 60% higher than a conventional system. So that's where, my favorite client is a long-term thinker that's more concerned about not initial construction cost, but the life cost of his structure itself. And that's why I think I'm doing a lot of government buildings, school buildings. They'll be up 15, 30, 40 years potentially. Some are built with lifespans of 50. That they're going to realize, there is a return on investment involved. You're going to pay a little bit more out of pocket up front, but typically with the rebates, and if it's designed properly, you can see anywhere between, on a commercial project, between a 1 year and a 5 year payback. On a residential, you're typically looking at between a 5 and 8 year payback, meaning it takes that long to save enough of your energy bills to pay for the additional cost of the geothermal system. But, another thing I use to sell as well is every time electric and gas goes up, you're making your money back quicker, and once that payoff is hit, you're printing money, if you will, compared to your neighbor who's buying gas and electric from Xcel constantly. The big challenge in Colorado has been is compared to the rest of the nation, we have relatively low natural gas prices. I mean, these systems they've really been embraced in the Midwest and back. Anybody in Colorado has propane, they're calling them, the phone rings off the hook because they're paying so much more. But nevertheless, again, it's that long-term mentality, what you're doing in the environment, what kind of structure you want to build. Back east, where people are still using oil to heat and cool homes, they don't even think twice about it. I mean, there's been a lot of retrofits. But retrofits are more of a challenge because I'm going to come in and I'm going to tear the hell out of your yard and your driveway, and that's going to be even more cost to replace and replenish everything that was torn up. So ideally, and that's why the majority of our jobs are new construction, because we're able to get in there on a raw piece of dirt and do our thing without causing any damage. Okay, so I talked about a plate and frame heat exchanger. This is a gentleman's residence up near Winter Park, and that's his pond he had in the backyard. We drained his pond about halfway down, and you can see we're craning in a stainless steel plate and frame heat exchanger. As opposed to putting the slinkies in the bottom, this is another way to skin the cat. You just put a big radiator in the lake. And there you go. There it is. There's another one we did up at a ranch in Aspen. And you can see it's just the radiator. It's just 4 radiators tacked together, and we sit down, we anchor to the bottom of the pond, and let it do its thing. Okay, and I'm going to finish with probably what's one of our favorite jobs that we did design and install. This is the City of North Glen Wastewater Treatment Facility, the wash basin slinky loop. What we did on this job, and they came to us and they wanted to do this, and they said, guys, in these wash basins, they're going to be full up to the top with basically water that's basically 50 degrees year-round. It's their aeration basins. That's sort of cleaning the refuge, or if you will, the sludge. And so what we came up with is rather than drill, rather than dig, we just built a series of stainless steel racks, hung our coils in there in each one of these, and as it's filling up here, we're using these. There's actually 3 of them because one's always down for cleaning while 2 runs, and so we did all 3, so there's always 2 heat exchangers available to heat and cool the building itself and the facility. And that's how it ended up working out. I lectured my guys really hard on this. That, I kind of nicknamed that the poop loop, and that they better do that. And that I kept the name of the guys who fuse it together. If anything ever fails, they're getting back down in there and fixing it, because I would not want to go anywhere near that. But knock on wood, it's been out 6 years and there's never been any problems at all. And that's the other thing to be said is with these systems is once they're installed correctly. Very, very few, small failure rate. I mean, what can go wrong with plastic pipe? It's buried in water, buried in the ground. Heat pumps, the only thing that goes wrong with heat pumps, if you get air in the system, they'll lock out on you. You got to hit a reset switch. The largest, most difficult part of it, and I knew this from a general contractor as well, are the controls. It's how the thermostats are talking to the heat pumps, are talking to the fans, and that's always a control issue that has nothing to do with the performance of the heat pumps or the loop field itself. It's just a matter of working through those. So when everybody calls me, that's the first thing I say is like, okay, let's go look at your control and how this thing's programmed and making sure everything's communicating with each other, how the pieces of equipment are communicating properly. The reason I was invited up here is because of the Mirasol project. That's a housing project that it's all geothermal. We have quite a few of those apartment complexes, elderly retirement complexes, Josephine Commons in Lafayette, quite a few residential high-end projects like that, even low-income housing in downtown Denver that's run off geothermal heating and cooling.
You know, most large office and school buildings, there's an index of, you know, how much energy they use per the size of the building, per square foot. And what Poudre Schools has accomplished with the Kennard building, in large part because of the efficient heating and cooling, is that they use about a quarter the energy. They have a quarter the energy budget, if you will, for that school versus other similar-sized schools and whatnot. So, you know, this is an important technology that delivers heat and cool a lot more efficiently, certainly than, well, than boilers and electric baseboard heating and that sort of thing. I guess what I wanted to talk to you about are a bit of the backdrop, the background for what the local utility is doing with energy efficiency and solar, and then to talk a bit more about some of the details and questions that you may have, in particular about residential or business solar installations. I handed out the handout ahead of time just so that there are some small graphs and whatnot that I want to walk through a little bit, but I think the main thing is on the back are some online links to get additional information about our city programs. One of the things that's available out there is, this is just the cover page, but our sustainability office here in Fort Collins produces at least every other year, if not every year, I think, this status report. And I guess policy and action related to the climate question for Fort Collins goes back quite a long time. You know, many of us recall that there were early international activities around climate change with the Kyoto meetings in 1995, and Fort Collins was pretty well in line by about 98 or 99 with their own city policy. And the folks that continue to, with city government, that continue to track our progress and the possibilities have been at it a long time. And the Fort Collins utilities in around 2003 put in place an energy policy to begin to try to encourage adopting, you know, more efficient energy use in homes and buildings, these kinds of technologies like heat pumps and just better design. And as I said at the outset, along the way, in addition to participation in the Medicine Bow Wind Farm, which is just up north of us in Wyoming and has been there since 1998. There's been expanded involvement in wind farm activities around the region and more recently local solar incentives. But, you know, I guess the question of you know, our modern day energy use and the side effects of it, what we know to be the potential greenhouse gas issues. Mr. Denning is a master at being able to describe, you know, really what's going on there. You know, when you get the so-called greenhouse gases in the atmosphere, they're able to, you know, he does a pretty good little dance about, you know, just what's going on. Well, these molecules, CO2 and other actors in the air are just absorbing energy and holding it. And you know, it literally is the greenhouse effect. That's pretty easy to understand. So the notion is, how do you burn less fossil fuel and so forth and so on? Well, the good news is that change is possible. And the first graph that I included here is our local tracking since 2005. The most recent version of our city policy is to try to head on a new trajectory so that city greenhouse gases are tapering to be 20% below what they were in 2005 by 2020, and lower yet in years beyond that. It's pretty much the same goal as we have at the state level, and many other communities, at least in North America, have set similar goals. Well, historically, and well, when I first came to utilities here, as I said, 6 years or so ago, if you looked at energy use in Fort Collins, it was steadily going up and up and up. Well, population was growing, the community was growing, and energy use was going up, but it wasn't going down at all. It wasn't looking like it was going to go down. More recently, since 2007 and 8, of course, we have seen the economic shakeout here in the country. But if you look at these graphs, the green line, if it's visible on the chart, is our aggregate tracking of emissions due to energy use and waste and everything. And the encouraging thing is the community has turned a corner, and that trend is down. So there was even a bit of concern, how could you introduce effective programs that really would alter that trend towards just more and more consumption of fossil fuels, more greenhouse gases, and so forth. The other two curves there are important to note as well, though, that the emissions have gone down while there's still been a continued slight trend upward in population. And after the worst effects, if you will, of the Great Recession, even economic activity is up, and yet we're still on a trend with the various programs to reduce waste, recycling and waste diversion and that sort of thing. We're encouraged that something can be done to actually take us on a trajectory down. So as a community, Fort Collins, I would say, has been stepping up to this question. Obviously, communities are composed of folks, you and I. So it also comes down to where we stand, what we may be able to do individually. This chart that's over here on the window ledge and the small version of it on the page, if you go home and look at your utility bills for, say, a typical winter month and a summer month, or if you get really enthusiastic, you look at the previous 12 months, and come up with what you think is the average kilowatt hours of electric use. Take this handout home and look up where you fall. On the lower axis, you start with a number that's going to be perhaps 800 kilowatt hours a month on average. That's pretty typical. And that'll take you up to the curve and across to the 50% point, because 800 kilowatt hours a month is about average use. If you find that your use is further out, 3,000 kilowatt hours a month on average, we have homes of that sort, that means that most other households are using less than you. And if you're way down here on the low end of the scale, maybe 300 or 400 kilowatt hours a month, then you're probably in the lowest 20% of typical electric use. Why is that of interest and important, besides just the fact that you can identify where your average use falls? Well, first of all, gains in reducing greenhouse gases usually and most cost effectively start with looking for efficiency, tightening up your home. If you're building a new home, you may want to consider something like a residential geothermal heat pump system or other systems. As we've indicated, it's maybe an expensive option if you have an existing home, but there are other things you can do, and those are usually the cheaper things to start with. The other thing is, if you go to the two charts at the bottom of the sheet, it's probably obvious enough that if your usage is high and you're thinking about, you're wanting to consider whether rooftop solar is an option for you, the higher your use, the less offset, if you will, of your electric bill that solar system is going to produce if your usage is high. So if you can bring your use down, it just becomes a system of a certain size is going to be offsetting a larger fraction of your use if you can first work on how much electricity you're using. There's a tool that we at Utilities that we've developed, which is a home electric inventory. And it is one of on the back, at the bottom of those resources is something listing the environmental program series. And you can find a link to this home inventory there. And if you have trouble finding it, I'll have some business cards and happy to be able to send copies out of those that are interested. But you basically can, in maybe 10 minutes, walk around your house, look at how many light bulbs are in the fixtures, how many things are plugged in the wall, what's the array of kitchen appliances, what's on the workshop shelf out in the garage. It's all of those things you tally off, and then the tool will summarize. Well, is it all of the lights in the house that really are your biggest use and maybe the thing to pay attention to, or is it your air conditioning? What is it? So it can be a good, fairly directed exercise to figure out what's using electricity in your house. Because once you have a sense of what's using electricity, then you can potentially think about what to tackle first and move yourself down the curve. Because then, just by the several hundred solar homes that we have in Fort Collins, the average size of them, the way that they measure the size of a solar system is by the peak output that it will give you on a bright sunny day. The average is about 4 kilowatts. A 4 kilowatt system, if it were running at that level for an hour, will give you 4 kilowatt hours of energy, for what it's worth. But that chart on the lower left, if your average monthly electric use is a number like, say, 700, then a 4 kilowatt system will offset maybe a little more than 60% of your electric use. It'll provide that fraction. If you're lower down on the curve, say at 350, it'll produce more electricity than you use. So that's kind of the trade-off. Another way of looking at it is the chart on the right, that as you go up from low to higher and higher use, how large a system would you need to invest in to offset 100% of your use? And you get out to, say, 2,000 kilowatt hours a month on average, and that's a number like something like a 16 kilowatt system. And that takes a lot of roof to, or a big backyard, I guess, to put a 16 kilowatt solar system on your property. So it is a balancing game between doing the things that are, hopefully some are easy and inexpensive, and other things that are more investments perhaps in your home to tighten things up, consider beefing up attic insulation and that sort of thing. Again, on the back with the resources, I want to draw your attention to one that's the fourth one down, home efficiency, which is basically the utilities home efficiency program. Many of you, how many people have actually taken advantage of the home energy audit? I see a few hands. The utility has set up and sponsored a very good diagnostic home audit and subsidizes the cost. It's $60 to you, or $50 if you find the coupon that's out there for it. And that would otherwise be something like a $300 energy audit with a blower door test, which verifies fairly definitively how leaky or tight your home is and where the leaks are, and then also with an infrared camera helps pinpoint where those leaks may be. And then, of course, the notion of that exercise is to suggest, well, what are the best first things to do? And often they can be fairly inexpensive. A few $100s of air sealing year after year can the payback on that can be easily within a year or two in some cases. So the other thing that I wanted to give you for perhaps your own home study later are a few of these rules of thumb related to solar technology, you know, the place where most of us will start is with talking to a solar installer and getting some information, getting their estimate of how much you can put on your roof and so forth. These are just some guideline numbers that may help you kind of do your own back-of-the-envelope calculations to verify and double-check what you may be hearing from a solar installer. There's an indication of how, you know, for 1 kilowatt of solar capacity, how many kilowatt hours a year are you likely to get? If you put on 4 kilowatts or more, then it goes up proportionately. These days, that number of $4,500 per kilowatt is sort of a ballpark number of what the raw or, you know, sort of unadjusted cost may tend to be for a solar system. So before federal tax credits and things of that sort, you may be looking at a quote of $14,000 to $15,000 for perhaps the next 3 or so years, a 30% federal tax credit, which is available for solar, and Fort Collins Utilities currently offers a local incentive, which is about, in round numbers, about another $5,000. So for a few $1,000 investment, you have purchased a system that this is now these days a good, solid, robust technology system to pay for itself. On the other hand, it is a way to get, as you can see from the charts of how large a system you might need to offset all of your use, you basically are generating, you know, your kilowatt hour use from, you know, the sun. And so even though in almost all cases people remain connected to the grid, and that's the source for the electricity for you know, your lights in the evening and so forth, it's possible to have a solar system that can be, if your usage is, especially if your usage is down on this use curve, that is offsetting 100% of what you're using, and that may become more important as time goes on, as we're all looking for ways to trim the electricity that has to be generated by Rawhide Power Station, which is north of here, of course, and is a main supply of power to this community, and it's a coal-fired power station.